I did lots of mathematics and science from drawer over the years, and I started to compile the list. I mean, so when I was in graduate school at Yale, I spent a lot of time reading his foundational paper on Vassiliev invariants, which covered so much ground. So that was eye-opening back then, and I think it's still eye-opening now. And also later, I want to say, drawer gave an enormous contribution to link homology, which really attracted people and developments into the field. He wrote two foundational papers on homology. So the first paper, first of all, it gave sort of, it was, as he himself said, that it gave an elementary definition of link homology accessible to curious high school students. Later this led to REEs, or high school activities on link homology. And it also really started the field because until Drore's work, there were no computations of link homology beyond some trivial cases. But Drore told us that for most small links, homology lies on two diagonals. And so later, and Sudi, I think, motivated by his result, computations, and Sudi proved that's the case for all alternating links. And later, this led to, fairly quickly, it led to Rasmussen's work on link homology on the Rasmussen invariant, which kind of showed useful applications of verification of Jones polynomial to 3- and 4-dimensional topology. And so second paper of Drore on the subject had many foundational discoveries. So it's Canopodis, operatic language for link homology. The skein relations on surfaces and are free behind the link homology theory, and his realization that the Frobenius algebra relation x = 0, where the state space of a circle of the unknown is two-dimensional over the ground ring, and corresponds to the Frobenius algebra with this defining relation, gets deformed into x² is hx plus t for generic h and t of degrees 2 and 4. This also allows one to rephrase the Rasmussen invariant using a version of this theory with h = 0. So I think that, just the paper is full of gems that were foundational in the development of link homology in the following 20 or so years. And I also want to mention many other things. I should mention the Bible code, work on the Bible code. And there are just gems spread out through his research and slides. So, for instance, he had very interesting result and observation on how to, if you're looking at a map, how to go from one point to the other point in the least distorted way. Another thing that I enjoyed learning from Drore a number of years ago was he has a video and slides on the Kolmogorov-Arnold representation theorem, which roughly says that a continuous function of many variables can be written as a composition of functions of just one variable and additions. And more recently, there's been a lot of interest. And so this is theorem back from 1950s. It's a collection of theorems. And there are, in the last few years, there's been very interesting developments about people trying to adopt this construction to a new viewpoint and approach to neural nets. So let me mention Kolmogorov-Arnold networks. Next. And you can look this up in the papers of Tegmark and a number of his collaborators. And very recent papers that I was surprised to discover very recently, 4 papers by Mike Friedman. Mike Friedman, he has papers where he says that the proof of the Kolmogorov-Arnold representation theorem reminds him of what you see in neural nets, where a lot of functions have various minors for the partial derivatives close to 0. And apparently that's also a feature of the construction of functions in the Kolmogorov-Arnold representation theorem. So I recommend you these 4 papers. Just have to be a little bit, you have to make some effort to find them in the archive, because the archive is not perfect for searching names. And so this specifically for continuous functions was fails for smooth functions. When I asked Dror about recent papers by Friedman, Dror said that Friedman is his kind of some of his main papers are about continuous four-dimensional topology and not smooth. And this is similar somehow conceptually. Perhaps he's interested in this Kolmogorov-Arnold theorem because it's also about continuous functions. It doesn't work for smooth functions. But Dror has a video from, I think, over 10 years ago on this representation theorem, also relating functions that appear in the construction to chocolate bars. So I recommend you the video and exploration. It relates to very fashionable technology nowadays, neural nets and artificial intelligence. I think that's an interesting future research to look into. And today, I want to talk about simple things and talk about the Delannoy category, which is a joint work in progress with Noah Snyder. It's a paper in progress, and it's also most of the work and introduction to this Delannoy category can be found in the papers of Harman Snowden, Nate Harman and Andrew Snowden, together with a joint paper with Noah Snyder, where this category is understood in detail, and related papers of Sophie Chris. So to me, the Delannoy category, it gives one answer to the following question. So suppose you have a functor f. So how would you form f choose n? So f choose n. Well, if you have a parameter t, you can form t choose n, which is t minus 1, t minus n plus 1 over n factorial. So the simplest example would be t choose 2, t minus 1 over 2. Question is, can you do this for functors? And this is encoded inside this Delannoy category, such a construction. And why do you want something like this? I mean, first of all, what does it mean on the level of functors? So if parameter t becomes a functor, so then given a functor f, you want some additional conditions on f to be able to form the functor which has the following shape or image in the Grothendieck group, f of minus 1 over 2. What does it mean? If you call this functor f f2, and what you want is for f squared to be isomorphic multiplied by 2 copies of f2 plus a copy of f. Particularly, you want to be able to take square of f, and remove a copy of f, and divide by 2, so to form functor f bracket 2, and so on for all n. And why is this potentially useful? Potentially useful because in the integral form of SL2, of the algebra SL2, you have generators E, F, and H, and the integral basis is formed by elements of the form En, H, Hn, M, Hn, where e to the m over n factorial, and H, I'll just write to the n, is given by this formula. So when you're doing homology, I mean, so in the theory of quantum invariance, we often have some representation of the quantum group. You tensor R, different action of, on one hand, of braid group R, and on the other, the action of some quantized D algebra. After clarification, the tensor R becomes some category, mu sub R. This becomes a categorical action of the braid group, and this becomes a categorical action of some version of this quantum group. And so one feature of this categorical quantum group is that you don't have Cartan anymore in this categorical quantum group, and in this construction as well. The Cartan is replaced by just projections onto the integral weights. So you don't really have these elements, you just have these two elements together with a projection onto an integral weight before and after verification. So if you look at the clarification of quantum group story, what it's lacking is clarification of elements of the carton, clarification of elements of this form. And it's one feature of the Delannoy category is that you will find a sample clarification where t choose n become functors. I'll explain that. That was my interest in learning about Delannoy category from our collaboration. And to explain the Delannoy category, and it also has a graphical calculus, which let me explain it as follows. Let us take an oriented interval and put labels, variables x1, x2 at the endpoints, and say that this oriented interval corresponds to the inequality x1 less than or equal to x2, where our variables xi are real numbers. And I want to think of this interval with orientation as delta function of this region. This is a region in R2. R2 with coordinates x1, x2. So I think of this as a function, so it's an element of the function from R2 into some ground field K, pick any field K. It's a function that's equal to 1 on this, in this region, and it's equal to 0 otherwise. And let us now compose these functions. So let me explain the composition. So we want to group these intervals together. So from x1 to x2 and from x2 to x3. And when we compose them together, we have this what we call an inner variable. x2 is now in the middle of a diagram. And we would like to integrate over it. So we have the delta function x1 less than or equal to x2 and delta function x2 less than or equal to x3. And we would like to, so these are kind of outer variables on the boundary. x2 is the inner variable, so we want to integrate over x2. And if you look at the inequalities, it tells you that x2 belongs to the closed interval from x1 to x3. And so our integration is going to be integration over the Euler characteristic. So we compute possible range of the values of x2 and take the Euler characteristic of that region. The Euler characteristic is 1. It's 1. So in fact, this is just the delta function of x1 less than or equal to x3. And so this is, it says that this element is an idempotent in the following sense. If I call this element e plus, then this integral computes e plus squared. And we get back the same function, except that the label has changed on the boundary, but that's a minor thing. So e plus is an idempotent. Now, likewise, you can look at the oriented interval going in the opposite direction from orientation.
Convolution algebra, yeah. So which algebra structure?
Yeah, it's just you compute, you take intermediate variables, look at the region where they are, and you take the Euler characteristic, but it should be compact Euler characteristic. I'll give an example soon for that. So that's just it. It's just convolution using the compact Euler characteristic. So let us look at orientation going back, so that x2, now it's x2 less than or equal to x1. So if we, let me call this E minus. And again, E minus is an idempotent. And let me go like this. So this is x1, x2, x3. So now orientations are opposite. So we're taking E plus times E minus. So we'll be looking at the delta x1 less than or equal to x2 times delta x3 less than or equal to x2. And we should integrate over x2. And now x2, the x2 is greater than or equal to the max of x1, x3. And it's like as less than plus infinity. So x2 is in a semi-open interval from this max, let me write it as m, max 2 plus infinity. So this is a semi-open interval. So its OI characteristic, compact OI characteristic is 0. For the compact OI characteristic, you need to compute T5, and then compute the OI characteristic of that compact T5 is minus what you've added, minus the compact part, minus the characteristic of the compact part that you added. So you write this as closed interval minus a point. And each one has OI characteristic 1, so the result is 0. So that's 0. So this is 0. It tells us that this to idempotent or orthogonal plus or minus is 0. Pure orthogonal idempotent.
Is this algebra commutative?
So let us for this particular example, yes. For one boundary point on each side, it's a commutative algebra. Now, let me also introduce a dashed line oriented from x1 to x2 to mean delta of x1 less than x2, strict inequality. And if you were to do similar computation for the composition, dashed line from x1 to x2 and from x2 to x3, and you're composing this function with the same function. So again, you're computing square of this element. And if you do it, you integrate over x2 in the open interval from x1 to x3. And the OI characteristic is minus 1, because you need to, it's minus 2 points. So the OI characteristic is 1 minus 2, it's minus 1, so you get a minus sign. So this is square minus delta, so it's minus and idempotent. So let us come back to those idempotents. We see that they are orthogonal. And they actually give us a decomposition. And to explain the decomposition, in this case, let me first say in general. In general, we're going to look at functions on Rn. So we have n. You can think of a network built out of these pieces, which has n outer variables and some number of inner variables, and we integrate over the inner variables in this way. But in Rn, we have variables x1, xn. On R, there is an action of the group of homeomorphisms, which are orientation-preserving homeomorphisms. Let me call this group G. And there is induced action of this group on Rn, acting on all coordinates at once. And this action, for any n, this action has finitely many orbits. And the orbits have the following form. So you write your x1, xn. And then some of them may be equal in the orbits. X1 may be equal to x4 or to x6. And then x2 might be by itself, x3 equal to x5. And then you need to say which numbers are less than the other numbers. You could say that x2 is maybe less than x3 equal to x5. And this is in terms less than these three numbers. So the orbits of the action are given by decomposing n elements into subsets, disjoint subsets, and picking a total order on the subsets. So these are the orbits of the action. And what we're doing, we're looking at functions on Rn, which are constant along these orbits, taking values in a fixed field. And so this is our space of functions. So when you have a complicated diagram built out of these things, then after you integrate the inner variables, you get an element here. And if you want to do it in terms of categories, you could say that you start x1, xn on one side, you have y1, ym on the other side. So you just split your set of variables into two sets for source and target objects. But of course, Droid will say that it's not necessary because you can just do a periodic formulation where you just have one set of variables, and either approach is fine. But let me use the version where you have sources and target variables, and then you look at functions on Rn plus Rn, smooth along with simplification, taking the reason k. and then it's f of x's and y's. And when you compose these functions, then you compose f with g depending on two sets of variables y and z. So you will integrate over y's using this compact characteristic as your measure. And in this way you get a category. So you get a category, let me call this category C prime. It's going to be a monoidal category. It has a product, has a generating object x, and you can form tens of powers of x such that the form, so by definition the form from xn to xm consists of all these functions. Functions on Rn cross Rm, which is the same as Rn plus m values in k relative to the stratification, and the composition of morphisms is given by this integration of intermediate variables.
For those functions there, you're looking at g acting simultaneously on both Rn and Rm, yes?
Yes, so g acts on R, and it acts on Rn, and the action has finite for any n, the action has finite in many orbits. And it turns out that people study this kind of actions, they're called oligomorphic actions. Oligomorphic actions where you have an action of usually an infinite group on an infinite set such that the action on any Cartesian power has finite in many orbits. And then in the work of Harman-Snowden, as we mentioned, Harman-Snowden, so they look at oligomorphic measures. Oligomorphic measures, this is an example of such a measure. It's a measure given by the compact characteristic, but it has some nice properties, non-vanishing properties, which allow them to build this category, such a category. And here we should take C prime, and then just take the Karoubi envelope of C by adding finite direct sums of objects and adding idempotents. Idempotents give you new objects, which are projections onto this idempotent. In the work of Harman, Snowden, and Snyder, they study in detail this category, and their theorem is that the Karoubi envelope is a symmetric monoidal, of course, symmetric monoidal. And the important thing is semi-simple, rigid, semi-simple category. This is the important part. So it's rigid for simple reasons. Rigid, I would prefer to call it flexible. It just means you have cups and caps with isotopy relations. This is what the terminology is just the opposite of flexible, rigid category. That's kind of easy, and the hard part is semi-simple, saying that this category is actually semi-simple over any field K. That's not, that's far from obvious. Because in this category can be just this, we're finding dimensional spaces of morphisms. But what you want to do is look at the endomorphisms of X and M for each n and ask whether the algebra of endomorphisms is semi-simple. And in fact, it turns out to be semi-simple and just a product of matrix algebras over the field K. So that's the hard part of the theorem. But let me give you some flavor of how this is proved. So first, we have a relation that this is, I just want to say also that just a solid unoriented line from x1, x2 just means that they're equal, just equality. It's also identity. If you look at this convolution, this diagonal x1 equal to x2 gives you the identity map for the convolution. And so this is identity from x1, x2. We can check what it's equal to line going up. So x1 is less than or equal to x2. Plus line going down, the inequality in the opposite direction, minus this unoriented features where things vanish. So this just means that you have x1, x2, and x1 vanish, so sort of any x1, any x2, no relations on them. So the third term is the delta function, with x1, x2, no relations, and with the sign minus. Why the sign minus? And minus is because if you compose them in the opposite order, we get this bar. This bar means you just have x, variable x, with no relations on it whatsoever. So it's x in R, and you integrate over x. And as you integrate over R is topologically the same as an open interval. So the only heuristic is -1. So it's -1, and to cancel this minus sign, you add a minus here. And then this is the decomposition of the unit element into the sum of three mutually orthogonal idempotents. This is E plus, this is E plus. You know that E minus is orthogonal, E plus. This is plus everything else. The third idempotent is everything else. So it's 1 minus E plus minus E minus. It's also an idempotent. It's orthogonal to the other two. And you can also see that it's a decomposition of the diagonal as a sum of those three functions, delta x1 less than or equal to x2 plus delta x1 greater or equal to x2 minus just the constant function on the whole R2. And these three are orthogonal. And again, for instance, orthogonality between these two. Let's say we'll do this from x1 to x2 less than or equal. And now it's make x2 in the variable. So it's anything. Integrate over x2. So x2 is in the semi-open interval, x1 to plus infinity, the integral is 0. Which is part of the orthogonality properties. And this relation tells you that the endomorphism of x is a product of three copies of the ground field. Multiples of E1 times multiples of E2 times multiples of the third idempotent, 1 minus E, 1 minus E2. And the endomorphism ring is three-dimensional. It's three-dimensional because we're just looking at functions on R2, which are constant on the orbits. And there are three orbits, x1 less than x2, x1 equal to x2, x1 greater than x2. So there are three orbits. So the space of functions is three-dimensional. So it's some ring. There are not many rings which are three-dimensional, but there are some which are not semi-simple. But in this example, this ring which shows that it's a product of three copies of the field K. So it is semi-simple. So the theorem of Arnold and his neighbor extends this to X tensor n, showing that all of these rings are products of either fields or matrix algebras over fields. So why do they call this Delannoy category? Well, for the following reason, which is not convincing to me, but when you study this X tensor n, ultimately you want to get to simple objects. The simple objects end up being very small, in the sense that X tensor n is the sum of these objects with very large multiplicities. The objects being very small. But as a first step, they can do crude decomposition and reduce it to x to the k, where x to the k is an object where you say, well, I just in the diagonal on Rn plus Rn, the diagonal space, just take a subspace corresponding to one of the orbits of Rn. So just take the orbit, x1 is less than, say, x2, etc. less than xk. N. So you just put these unoriented lines, so it's x1 on the other side, x2 on the other side with the equalities, but just put strict inequalities here in one of the possible ways. So this is just crude decomposition of X tensor n into sum of x's for the orbits of the epsilon on Rn, not on Rn square, but on Rn. So this is sort of the first step. And these objects, they further decompose into sums of something more interesting. But for this object, if you look at Holmes from X m to Xm in this category, you can check that the dimension of Holmes is given by the number of Delannoy paths. Delannoy paths, so these are paths in the n by m rectangle, paths from the bottom left to the top right, which go to the right, up, or diagonally. to now Delannoy path, so either one step to the right or diagonally or one step up. And you can just prove this by looking at the functions of the product of these two orbits and counting the dimensions. In how many ways can inequalities on axis and on y's overlap together. We get this number. So this is just to tell you why it's called Delannoy category. But they're more interesting. They're kind of much more. Now, well, this is a much more refined decomposition, because here you actually get simple summons, and now you have these orientations on lines. And so how do you get the direct sum decomposition when you take tens of powers of x? So it turns out that you use the following construction. Let's look at the following diagram. Take Q, this is x1, so maybe y1, x2, y2. And let us look at this diagram encoded by the delta function. X1 is less than or equal to y1, less than x2, less than or equal to y2. So we introduce a chain of inequalities where we alternate between strict and non-strict inequalities, less than or equal and less. And let me also encode this diagram by a box with plus because orientations are upwards at the endpoints in some sense. Now, what is the use of this delta function? And the corresponding idempotent in plus. You can check, and it's a computation which I will leave as an exercise, that the square is itself, which means you take this picture, stack another copy of this picture onto itself, and integrate over y1 by 2. And you can check it's not important. Another thing is that this is orthogonal. Here you have 4 endpoints. And it turns out that this picture is orthogonal to most of what you can put. You can put each one of these idempotents at any of the 4 endpoints. So there are 3 choices at every endpoint. For instance, you can take the upper right endpoint and put ended here, say, well, I'm going to make this endpoint inner. So just integrate over y1. But if you integrate over y1 satisfies this half strict and half non-strict inequality. So y1 is in the semi-closed interval, semi-open interval from x1 to x2. And as you integrate over this interval, you get 0 because it's semi. So if you make this variable inner, say that it's not on the boundary anymore, then you get 0. So putting a dot at this leg gives you 0, and likewise at any other leg. The fact that if you put a dot at this bottom left leg, that it's 0 is because you're now integrating over x1, which is less than or equal to y1, but greater than minus infinity. And that's again a semi-open interval. So you're using the semi-open intervals to kind of create something which is orthogonal to many things, because those integrations give you 0. So this is 0. And also, if you put the wrong orientation, if you say, oh, I want to have orientation going in from in the other way, and now this is again inner, and you integrate over this inequalities. Again, you get 0 for a very similar reason. So if you put a down orientation at any of the 4 vertices, you get 0. So the only way to have this idempotent play nice with the idempotents we wrote down there is to orient everything up at each of the 4 endpoints. So this idempotent E++, it respects the decomposition at every endpoint into those 3 idempotents, in the sense that only one idempotent gives you non-zero. So only this choice gives you non-zero. So non-zero, this is another way to write E++. So it turns out that it's a minimal idempotent, and it gives you one of the minimal, gives you one of the simple objects of the Karoubi envelope. And there's also, so they have a formula for all simple objects. So all simple objects are obtained in the following fashion. So you pick a instead of two vertical lines, which are solid, you start with several lines. Oriented either up or down. And with labels x1, y1, y2, x3, y3, up to xn, yn. And now you connect this by dashed lines so as to create an entire uninterrupted oriented chain. So you connect this to here. Say y1 is strictly less than y2, just to have an oriented chain going all the way, oriented in the same direction. So here we need to make a dashed line go this way. Again, to continue to keep the orientation looking in the same direction along the chain. And here we need to put orientation here, less, and finally add this dashed line here. So this is a chain of non-strict inequalities and strict inequalities on the foreign two variables at the endpoints. So for every sequence of signs, in this example, signs of plus, minus, minus, plus, minus, each of this epsilon gives you, and you can check it as an idempotent, which I call E of epsilon. You can check it as an idempotent. It's sort of most of the time, if you put something here, one of the idempotents, you get 0, unless you put down or up arrow, matching the orientation. So the idempotents, they annihilate each other, and they are exactly the minimal idempotents. So the theorem in Harman, Snowden, Snyder is that any E epsilon over all sign sequences epsilon are irreducible objects, or all give us all reducible objects of the Karoubi envelope of C prime category E. So in particular, there are lots and lots of simple objects. There is one simple object for every sign sequence. For the empty sequence, you just get a corresponding object used as just the identity. The functions on a point. Then for one point x, for the object x, capital X, you have this decomposition. So let me just try to say that we know the corresponding object x of epsilon. So for a single strand, that expression gives a decomposition into x plus x minus plus a copy of the unit element identity object. Okay. Because in the center, in the middle, you go through nothing, so you project onto a copy of the identity. And of course, it gets more complicated for tens of powers of x. But the theorem is that these are all the simple objects, and any object is the sum of these objects. The category is somewhere simple. And in particular, if you take x plus squared, but you see that the number of objects goes exponentially with, as we decompose x tensor n, exponentially in n. But I promised you a category which where expressions of the form teachers n a category phi. So it turns out we should look at these diagrams where everything is oriented up at the bottom and the top. So just take the subcategory generated by x plus. So we can take its tens of powers. And then so it turns out that if you take x plus squared, it's going to be x q x plus plus x plus. So x plus squared, its tens of powers behave in decomposable sums, irreducible sums behave in this way. So take C plus subcategory, tensor subcategory generated by x plus, and also tens of powers. And it turns out that when you take x plus tensor n, you will only see x simples for the sequences x plus k times, where k is less than or equal to n. And it's going to be a sum of these elements with suitable multiplicities. And this multiplicities exactly match these binomials in the sense that it's a theorem, take the Grothendieck ring of the plus, and it's isomorphic to the ring Z. So Z adjoint binomials t choose n greater or equal to 0. And so what I mean here is that take the ring Q of t and consider the subring, which is the span of the binomials t choose n. You can think of this as the ring of integer valued polynomials. So there's a polynomials f in here, such that f of n is in Z for any n. So for example, polynomial t minus 1 over 2 is integer valued, because for any integer t you get an integer. And in fact, this subring, this ring has a basis of elements t choose n. And we're saying that the Grothendieck ring of the subcategory C plus just tens the powers of x plus and their sums is exactly this ring Z t choose n and the image of the object x plus n in the Grothendieck group. So gives you t choose n. So for example, for the second square, we get the form of the x plus squared minus, this is the problem, x plus over 2 is x, so to some quotes, is x plus plus. And likewise for higher tens of powers of x plus. So we get that. This is just an observation that inside this category, this big Delannoy category with very large exponentially growing Grothendieck ring, there's a much smaller category where on the boundary things are oriented upward. And this much smaller category is also semi-simple symmetric. It's not rigid. It's not bendable because the dual of x plus is x minus, because you can just bend an upward strand to go down, and so this is plus, this is minus. So it's not rigid, but it's semi-simple, symmetric monoidal, and the Grothendieck ring is this ring of integer valued polynomials, which is also the integer form of the Cartan, or the Cartan subalgebra of SL2. And I mean, so for us, I mean, it's interesting because one can hope that maybe this kind of categories can be extended to a categorification not just of the Cartan, but of the whole integer form for SL2, and perhaps later modified to categorify quantum groups, quantum UQSL2, and other simple algebras. It's the first step. But what's interesting is that we taking this very small subcategory from the Delannoy category. But the Delannoy category is a prime example of the theory developed by Harman and Snowden of oligomorphic categories. Categories that come from suitable measures on orbits of actions of oligomorphic groups. And I think this is a very recently discovered theory, which you can read. They have, Harman and Snowden have a very long paper about this and follow-up papers. So for our unfinished paper with Noah Snyder deals with diagrammatics for this category. In particular, this is a picture for the minimally idempotent. But in a sense, the minimally idempotent, they're not very complicated. They're just given by these pictures. And so this is a sort of advertisement for this area of oligomorphic categories which I think is very promising, but not many people are working on this yet. But so for us, we just want to borrow some ideas to hopefully build more examples of this form, not necessarily coming from enigmomorphic categories, but with the goal of clarification of quantum groups, where you don't have to use projections onto weight spaces and their clarifications. The idea is to try to clarify quantum groups in their more genuine forms without adding projections onto the weight spaces. And there's also a nice graphical calculus. So it's not a very complicated graphical calculus. You're just computing compact two-dick heuristic for very special functions, for very special subsets of Rn. So it's not a very complicated calculus, but it's still a graphical calculus that one can manipulate with. Let me stop here. Happy birthday.
I'm just curious, is it very difficult to generalize to Q binomial? Or?
I think there are some, this is more subtle, but there are some papers where people look at the quantum version, of this ring of integer valued polynomials. And there are also quantum version of the Cartan, but it's a bit subtle. It's in one of the papers of George Lustig going back to late 1980s. And there was also a thesis of my student who graduated, Alvaro Martinez Ruiz. He has some ideas for, independent of this approach, he has some ideas what to do for the quantum case. That is sort of a different viewpoint. But I think it's wide open. So this verification of quantum groups without having idempotence is completely open. I think it's a promising direction. I also want to point out that first, I don't know, when I was listening to Ruf's talk a couple of days ago, I felt like the algebra in one dimension that you constructed feels a little bit, I mean, on the informal level, sort of similar, because you have a finite dimensional supercommutative algebra for any odd number of pieces of the circle. And I think you also have idempotence, one for every vertex. And this idempotence gives you a decomposition of the algebra into product of local algebras for each vertex. But you have additional structures, which I think put them together. But there's some, on a very naive level, there are some similarities, but maybe just because of the presence of idempotence in both algebras, which allow you to decompose it into more elementary pieces. This is just for one-dimensional version of your study.
Other questions?
What is the motivation to get rid of these weight spaces? So would you like to work with more general categories?
Yes. Why get rid of the weight spaces? For instance, so in the original clarification of quantum groups, let's say the simple case, we clarify just the nilpotent subalgebra corresponding to the EIs, and then if you have EI, you also have EI to the n, and divided power, and in the usual clarification of quantum groups, you can clarify EI into functor curve EI, and then EI to the n over n factorial into the corresponding functor EI to the n. And this uses some Minkowski algebra. There's also some simple version of the story which has not been published. But here something similar happens, but you're able to subtract more things when you take tens of powers. So when you take tens of power of x times the square of x plus, you don't just divide by 2, you subtract. There are more reductions. You can subtract x plus before you divide by 2. So it's different for this ambulation, but it's a different story. But you're able to, you have more things going on. You can subtract more pieces before you divide by n. And I think it's natural to expect that you can clarify this. For instance, I mean, you can, for instance, because you might want to clarify modules which are don't decompose into integer valued weight space.
So for
example, that.
Like unrolled quantum group, for example, something which for example, it has complex weight spaces. So
exactly. Yeah, exactly.
Would you think you will have access?
Yeah, because I think, forcing to have projections onto weight spaces, I mean, reduces available representation. So you just have less, I mean, you're forcing yourself into more rigid structure. And in this example of harness node and sniper, you immediately have the scarifications of T choose n, binomial T choose n. So I think it's an indication there should exist scarification of quantum groups without adding projections. And I also think it's a graphical calculus in the spirit that drawer appreciates and likes. I hope that it's not a complicated graphical calculus, but it is a eye-pleasing graphical calculus. Also giving us some simple category view duals.
Let's thank Michael again.